Log on, tune in, find out. Another good idea from Cambridge.
At all to this audience. And one thing I don't have to say, because he's put it there, is that Tim is probably unique in the world at the moment in holding a chair in Oxford and in Cambridge as the Rothschild visiting professor here. Tim, we're very grateful to you. The only other thing I would say is I always wave this accurate timepiece here. It's the most accurate timepiece in the world for one specific task. It is, by definition, the Newton Institute Standard Hour. Tim, thank you very much, and over to you.
Thank you very much. Well, thanks, David, for that introduction, and thank you to those of you who braved the cold weather to come here. I guess I want to start, so my talk's got, in a sense, I'm going to start with a few general and perhaps slightly political remarks. Spend most of the time doing science. Take your time turning that over, David. And maybe finish with a few slightly sort of political remarks, which may fuel some discussion in our cocktail evening. Just to start with, I mean, I think, it is a fact, I guess, that the last year has been a difficult time for climate science. It's sort of a bit more than a year ago now that all that email hacking of East Anglia came out. And I think one is hard-pressed not to admit that Climategate has had a bit of a negative impact on the public's confidence in climate science. And arguably, I know people argue about this, but arguably did have a bit of a negative impact in the Copenhagen summit as well. But I think following on from that, and perhaps a more serious problem, has been the US midterm elections, where Obama has lost his majority in Congress, for example. And I think that is going to make it very difficult indeed for any significant progress that may or may not be made in Cancun to be put into legislation in the US, and probably that in turn will actually make the chances of significant progress in Cancun less likely. So putting that together, I'm thinking about this the other day. I feel that we may not like the argument that I'm about to give you, but I think we have to recognize that this argument does have substantial political traction in the world, and therefore is one that we have to take seriously. And that's the argument of the, well, I use the word skeptic, but maybe people object to that word, but the argument of people who say that the cost of significant global emissions cuts is just not warranted given the uncertainties that exist in climate science. So I'm not trying to argue that that is a good argument. I'm just saying I think we have to recognize as a science community that argument that cost of emissions cuts is too great and is not justified by or is undermined by the uncertainties that exist in climate science is one that we have to take seriously and engage with the people who make that argument. Now, that in turn raises the question, can we make inroads into reducing uncertainty in climate change? And that's really what I want to talk about today. So the basic question, two sort of sub-questions I want to ask, is are climate scientists, are we as a community doing all we humanly can to reduce uncertainties in our climate predictions? And there's a second sub-question, which is, are governments doing all they can, all they humanly can, to provide the sort of technology and infrastructure to enable climate science to reduce uncertainties? So there are two parts to this question, and in a way they can't easily be decoupled. But I think what I want to argue today is that we could do more, actually. If we had an end-of-term progress report, I think could do better, actually, is one of the arguments or one of the comments that could be made. So that's a little bit controversial, perhaps, to some people, but I want to argue about that. So, and then we'll see where that leads. So in my talk, I want to talk about some of the uncertainties, the science behind them, why it's been so damn difficult to reduce these uncertainties. Because if you come from another field, you might think, we've been banging on about uncertainties for decades, and If you look back at past IPCC reports, you might think very little progress has been made. So why is it so difficult to make progress in kind of refining our predictions down? After all, as I will show you, we have made fantastic advances in prediction of weather forecasting. This hasn't quite translated into the same improvements in climate forecasting. So why is that? And then in particular, what can we do? Now, I want to talk about one particular idea. I had in my abstract in my talk about I was going to talk about two things, but I realized with the Newton clock ticking, I probably don't have time to talk about both. I'm probably even going to get short on the first one. So I'm going to focus on one aspect, and I hope by the end of it you'll sort of see why things are difficult, but why things could move forward if there was the will, both in the science and in governmental circles. Just to start with, this is from IPCC AR4, showing a picture which I hope most of you are familiar with. Global warming, estimates of global warming, from the past and into the future, 2100. And these are different CO2 scenarios. So this depends on how much we, as a species, emit into the atmosphere in the coming century. But if we fix on any one of those, say A1b, which is a fairly middle-of-the-road scenario, although possibly we won't make A1b now, but that was considered to be a fairly middle-of-the-road scenario. The IPCC assessed that there was a likely range of warmings associated with that CO2 scenario by 2100. That could vary anything from less than 2 degrees, which we now think is a sort of level we might be able to adapt to over 4 degrees, which we think will be pretty catastrophic. So this is, this just demonstrates this range of uncertainty that exists. Okay, so why does uncertainty exist? Well, I put down a number of kind of key elements here, and things like, water vapor. The standard simple, even perhaps I would say simplistic somewhat argument is if it gets warmer, the atmosphere can hold, as it were, more water vapor. The word hold is a bit not correct scientifically, but let's say that. Hold more water vapor. Water vapor is a greenhouse gas, so that will amplify the climate change signal. In practice, it matters that we increase water vapor actually in the top of the troposphere, because that's where it really acts as a major greenhouse gas. Clouds. So water vapor, of course, is gaseous water. You can't see it, but it's transparent. It's opaque to infrared radiation. But clouds are liquid water droplets. You can see them, and clouds have a major impact in reflecting sunlight back to space. Again, the amplification of climate change by clouds, again, very much depends on the vertical distribution of that change in clouds. So an increase in upper tropospheric cloudiness may well exacerbate climate change. An increase in lower tropospheric cloudiness, say in the boundary layer, may actually offset climate change. And we'll see in a second that this is one of the main uncertainties about the future. We have things like ice albedo. As the polar ice melts, it exposes warmer underlying water, which absorbs more solar radiation. The methane clathrates, that's the melting of the permafrost, may release methane that was previously frozen into the permafrost, into the atmosphere. Methane, another potent greenhouse gas. Carbon cycle is to do with things like if the Amazon, for example, were to become unsustainable, maybe due to changes in precipitation patterns or temperature patterns. That then releases potentially lots of carbon into the atmosphere, exacerbating things. Aerosols. Strangely or perversely, maybe aerosols is an area where if we green up technology and reduce particulate pollution in the atmosphere, reducing aerosols may again speed up climate change. But I'm going to argue that the key, the major, all of these are important, but I want to argue the really substantial first order feedbacks that we must come to grips with if we're to really understand climate change are to do with the hydrological cycle. The interaction of anthropogenically increasing CO2 with the hydrological cycle, and it's the water vapor and clouds that are the kind of primary feedbacks. And indeed, if one reads, in fact, I've got a quote in a minute from IPCC, but they recognize these are the two things. If we can't get these right, then the others become very let's say, even academic. We've got to get these two right. I just start with a couple of animations just to show you that the atmosphere is a pretty complicated place. This is actually a satellite animation in the microwave region of the spectrum, which is actually sensitive to water vapor. So we're seeing one thing, that unlike CO2, water vapor is not a well-mixed gas in the atmosphere. It has regions, for example, in the desert regions, in the subtropics, where there is very little water vapor. And as a result, as most people know, you get these enormously hot daytime temperatures and enormously cold nighttime temperatures, because there isn't that greenhouse effect from the water vapor regulating temperatures. But this shows that it is a pretty sort of chaotically mixed gas. We see very nicely the mid-latitude weather patterns, which play an enormously important role in distributing heat from the tropics to polar latitudes. If it wasn't for those mid-latitude weather systems, the tropical oceans might end up almost boiling. So they play a key role in keeping things, as it were, temperate. And here's another satellite animation. This is now in the infrared part of the spectrum, I believe, IR. And they're looking at, we're now basically looking at sort of more liquid water. We see these, by the way, nice tropical cyclones. But really what I want to point out, this is over the tropical West Pacific, are these thunderstorms which are bubbling away, transporting heat and moisture from the warm sea surface temperatures into the atmosphere. And again, very kind of complex. These are very kind of complex circulation patterns. We're looking at something that isn't a nice, simple, idealized. Those of you who are familiar, for example, with Rayleigh-Bénard convection in a laboratory convecting fluid, this is something clearly much more complex and irregular and turbulent than that. So the water vapor, liquid water, are kind of complex, complicated substances in the atmosphere, and it's coming to grips with this complexity that is the issue. Okay, so I've got a couple of comments or quotes from IPCC, and I just make one general comment. People often, in the last year or so, I've had there's been this as a result of Climategate and everything else. A lot of people have come out of the woodwork to criticize IPCC and say, why is it such an alarmist document? There's so many uncertainties. Actually, IPCC has bent over backwards, I would say, to try to explain the uncertainties in our climate, in climate science. And so my general comment to people who are skeptical, I say, well, actually, have you read the IPCC assessment reports? Because you might find some of the things you think are being said are not being said at all. So they're very open, for example, about this whole issue of cloud feedbacks or cloud amplifiers. There has been no apparent narrowing of the uncertainty range associated with cloud feedbacks in current climate change simulations. A straightforward approach of model validation is not sufficient to constrain the models efficiently, and a more dedicated approach is needed. So two questions there. Why is a straightforward approach not sufficient? And what are these more dedicated approaches that are needed? I suspect, I didn't write this, I suspect the people who wrote this weren't themselves quite sure what a more dedicated approach meant, but it certainly meant we've got to do something a bit more sophisticated than what we currently do. And I'm going to try and suggest towards the end of the talk what that might be. Okay, now the talk is going to be a little bit like a sort of detective story, because I'm not going to give away where I'm going to, but I'm going to approach it rather sort of tangentially and circuitously, and hopefully by the time the dreaded clock has run out of sand, I'll have got somewhere near the end. So we're just going to do a little bit of history, and in fact start off by talking about weather forecasting rather than climate forecasting. This guy is Wilhelm Bjerknes. The Bjerknes family, he had a son called Jacob Bjerknes, who was also a very famous meteorologist and oceanographer. But Wilhelm himself was probably the first person to pose, if you like, weather forecasting as a real problem in mathematical physics. Rather than hanging seaweed out the window, whatever your favorite thing is, he said this can be tackled using the laws of physics. 1904, I think, the famous paper where he proposed this. So This is a classic, he says, initial value problem. If we know the laws of physics, which we do, the laws of the Navier-Stokes equations for fluids, the laws of thermodynamics, the continuity equation for mass, and so on. And if we know the initial value, initial conditions well enough, we can project forward into the future and make a weather forecast. L.F. Richardson, who's probably known to many of you, very sort of eccentric but remarkably innovative scientist, the person Mandelbrot, for example, acknowledged as the father of fractals in his study of why countries go to war with each other. Won't talk about that now because it'll divert us from the main area of the talk. When he was a conscientious objector in the First World War, but he nevertheless served on the front, taking people back to the field hospitals from the front line in an ambulance. And in his spare time, he actually did the first genuine computation of a weather forecast. So he took some observations of pressure around Europe, sort of extrapolated them into the high atmosphere, and did a calculation. It took him, I think, months, if not years, to do the calculation, and it was hopelessly inaccurate. But nevertheless, he set the basis, and indeed the basis is still what we use today. He had this vision, which he wrote about in a book, of a weather forecast factory with many thousands of what he called computers. Of course, in those days, this was the 1920s, I think, when he wrote it, a computer was a person. So you probably can't quite see, but this is a factory with many thousands of people who are all doing little calculations and passing them to their neighbors, and they're all the people, these people are representing the southern hemisphere, these people along here, the sort of equatorial latitudes, these people up here. Here's the director who shines his light at the people who are getting too slow compared to the others and so on. And I don't know what these people do, but there we are. So it looks like they're having a good time. This is a remarkably prescient, actually, vision of what is now would be called a massively parallel processor. This is exactly how a modern-day high-performance computer works. The individual chips are doing individual bits of calculations, and it's all put together in the high-speed computer. So Richardson's a very remarkable guy, very forward-looking guy. But the actual age of weather forecasting for real occurred shortly after the Second World War. And this is a team led by the very eminent mathematician John von Neumann, who many of you know from his work in fundamental mathematics and quantum mechanics and so on. But he led a team, this guy Jules Charney was the kind of leading meteorologist at the time, to actually put together a numerical weather forecast on a digital computer, these computers emerging out of the Second World War. This was a team based in Princeton. I'm told that von Neumann's interest in this project was less actually to do with forecasting the weather and more to do with modifying the weather. And the vision he had was that if you had a numerical model of the weather, you could calculate where to set off an atom bomb in the atmosphere to actually actively change the path of weather systems. So this had a slightly strange idea about why these numerical models might be worth pursuing. But in any case, I don't think that idea thank God, caught on, although I have to say a variant of it. But we'll talk about, I'm going off at a tangent now, so I won't do that. But this was kind of the start of the sort of weather forecast age. So here's sort of where we are now. This is based at a centre where, actually, in addition to Oxford and Cambridge, I spend also some of my time. A place called the European Centre for Medium Range Weather Forecasts. Our detractors call it Early Closing Monday, Wednesday, Friday, which is an easier acronym to remember. But what it shows is how the skill of weather forecast has improved, not since 1940 or 1950, but since 1980. So pretty much over the last 30 years. And we're looking at a metric. We've been talking about metrics, and metrics are awkward things and somewhat ambiguous, but this is a generally accepted metric for how far into the future forecasts provide useful information for people making decisions about different things. So in 1980, it was about 5 days, just over 5 days ahead, and that's improved over the years. And by the beginning of this year, well, in fact, for a period, it actually went up to 10 days, so doubling, more or less double, but perhaps on an average would be around sort of 7 or 8 days. Now, This improvement's come about for a number of reasons. One is the models that we use, I'll talk about shortly. But another is a key aspect of numerical weather prediction, which enables us to use observations of the weather and ingest them into models. Now, I'll talk about models. The computer models may typically have many millions or tens of millions, or even hundreds of millions actually, of individual equations. They're enormously complex. And when we want to initialize the state vector, the state of that equation system, we don't have as that many observations. We may have, let's say, 100,000 observations. So how do you initialize several million components of a state vector when you only have several 100,000 observations? So the process to do that is called data assimilation. This is something that Chris Jones talked about in a workshop earlier in the year, and I think it's been quite a focus of activity at this Newton Institute. So it's something I want to dwell upon for a few minutes. The basic idea is that we actually combine the observations essentially with our knowledge of the laws of physics for the system. So to be a bit more specific, suppose this is a kind of trajectory in state space describing some observations which have some errors. These are not perfect observations, have some errors. And I've made an initial condition here at this time. Now I use my knowledge of the laws of physics as encoded in my computer model to move that state forward in time to, would be just say 6 hours into the future to this point here. So now I have two sources of information, a very short-range weather forecast, 6-hour weather forecast, and data at that time. And data assimilation is a way of optimally combining those two sources of data to produce an optimal state. And the idea is that the errors on average of this new initial state are actually smaller than the errors associated with the observations. I'm doing better than just using the observations alone. So using the laws of physics in addition to the observations give me a better estimate of the initial state than just the observations alone. It's a problem in sort of control theory. One's minimizing a so-called cost function based on least squares method. There are some real problems to do this, notably the high dimensionality of the system. As I say, we're talking about tens of millions of degrees of freedom here, potentially sparsity of data. And in fact, doing this minimization, which I'm not going to talk about, but doing the minimization takes more time on the computer than running a 2-week weather forecast at very high resolution. So this is, if one had to say of the weather forecasting kind of cycle of things, what is the most computationally expensive? It's doing this minimization. By the way, for the cognoscenti, we'll recognize this is a slightly simplified form of the cost function, but we needn't dwell upon that. One really important thing, for example, that this does is enable one to ingest satellite data very easily. So satellite sits potentially tens of thousands, if it's a geostationary satellite, of kilometers above the Earth. So it's not measuring directly temperature or pressure or winds. It's measuring radiances in different wavelengths that come up well from the atmosphere up to space. So these yi are observations of radiances. X is the model's state vector, and H is what would we call a forward operator to enable you to go from state space to radiant space. So this would have Planck functions and such like in to get radiances. And then the minimization is done in that kind of observation space. And so what this does, as well as being able to fill in holes where there aren't observations, it's able to essentially invert this type of satellite information, which otherwise is quite a tricky art. And in fact, that's one of the main costs of the system to do this inversion of the satellite radiances. Okay, this will all slowly make sense as we move through the talk. And what's he doing there? Oh, yes. So I'm trying to impress you about how wonderful weather forecasting is. But some of you who are sort of at a certain age or more, I've decided you have to be at least 30 to know what I'm talking about here, will remember this infamous BBC weather forecast given by the weather forecaster at the time, poor chap Michael Fish. He basically said, don't worry, no hurricanes tomorrow. And sure enough, what happened was the mother of all storms. which overturned trees and cars and aeroplanes and various other things. The poor chap has never lived it down, although he tells me his main regret in life is never having copyrighted that weather forecast, because he said if I got a penny for every time it's been shown since, he'd now be a very rich man. So what that reminds us is there is, as it were, a fly in the ointment of weather forecasting, which was very clearly demonstrated by the famous meteorologist Ed Lorenz from MIT back in the 60s, and this is his famous three-component model. So this is now, typically this attractor, as it's called, which integrates these equations, appears as screensavers on your PC. So this is a kind of piece of trivial mathematics, if you like, from a computational point of view, although at the time when Ed was doing this work, he needed a state-of-the-art mainframe to actually explore the properties of that system. So the butterfly effect, you'll all know, you start off with two states which for all intents and purposes are identical, but sooner or later the differences start to amplify and diverge. And he used this as an idealized model of weather to show that long-range weather forecasting was, because at the time there was a lot of ideas about using statistics to do long-range weather forecasting, so-called analog methods. These were doomed to failure. We can sort of illustrate the butterfly effect in the context of Michael Fish's 1987 storm by looking at the weather as it was a couple of days before the storm hit. So here are two weather maps which are, for all intents and purposes, identical, but in fact they're not absolutely identical. And what we're going to do is run our weather forecast model forward from these. And what you see after a couple of days of integration is that one develops quite an intense vortex, and the other looks like, well, you're heading for a nice day. So poor Michael Fish, he drew that one. That's what the Met Office rather sent him across the wires to give to the people of the UK. Whereas if only that butterfly had been flapping, then and he was able to give this one, then of course he'd be a hero. Well, how strange things hinge on just flaps of butterflies' wings. Well, these days, of course, what we do is because this is a fact of the equations of motion. This is a scientific fact that sometimes small uncertainties in initial conditions amplify. So what do we do now? We would run what's called an ensemble. We run our model 50 times, and we look to see basically what 50 times from virtual identical starting conditions, and we look to see how what the distribution of weather patterns is. This is an exceptionally unpredictable situation where you can get these intense vortices in one solution and absolutely nothing at all in another one. So what would you do? You have to put this together in some sort of a probabilistic forecast. There's no way one can give anything deterministic or categorical about what's going to happen. But putting those individual stamp map forecasts together, we come up with a probability. So this is what one would hope a sort of latter-day Michael Fish would be able to do. Say there is a quantifiable risk of 40% or 30% of hurricane force winds hitting southern UK. Now, of course, that's an enormously larger probability than the climatological probability of hurricane force winds, which must be 0.00000 something 1%. So there's clearly a major kind of signal being forecast here, but it's not one can be certain about because this is inherently unpredictable. It's worth actually just going back to the Lorentz model because it illustrates a kind of key aspect of predictability in nonlinear systems, which the climate is, which is that predictability varies according to initial state. So if you have the Lorentz model, some initial conditions up here, you put a little error on your initial conditions and the error doesn't actually grow at all. So you can make a finite time prediction from this part of the attractor over here, which is extremely predictable. This you could think of as a slightly more normal situation where there is some spread in the final forecast state, in a sense of being able to give a probability. A situation like this where now if you like, this ensemble or this error is kind of hitting the really unstable part of the attractor, just produces this massively uncertain forecast, same forecast time as here and here. So this is very, very similar to the real weather system. Most times we are actually pretty confident what's going to happen a couple of days ahead. We can even say, as I showed you, up to 10 days ahead on many occasions. Sometimes we can only say things in a probabilistic way, and sometimes things are just utterly unpredictable, even in a very short range. And you know, it's a feature of the nonlinearity of the climate system that does it. It's a generic feature of nonlinear systems. I thought I'd just pass sort of slowly into the climate side by addressing a question which is often asked, and this is one of the so-called climate skeptic books which appeared in the last year or so, and this is, you know, a thing which people often ask: how on earth can we make forecasts 100 years in the future when, you know, Michael Fish can get it wrong 2 days in the future? And of course the answer is to remember that we're not really talking about an initial value problem when we're doing climate change. So if I was to run that Lorentz model out now, not just a few time steps, but many thousands of time steps into the future, I'll produce a very irregular, aperiodic kind of vacillation between the two lobes of the attractor, the positive X states and the negative X states. And there would be no predictive capability of saying at any instant in time whether the state was down here or up here. A tiny, tiny, almost infinitesimal perturbation to the initial state could cause, say, the state here to be from down here to being up here. But nevertheless, there's some sort of stability in the statistics of where the state will be at any moment in time. So if I were to freeze on this moment in time, I can say quite confidently there'll be a 50% chance of it being up here and a 50% chance of it being down there because of the underlying symmetry of these equations. It's a property of the kind of statistics of these equations. Now, what we're doing with climate change is not really an initial value problem. We're changing the composition of the atmosphere in a way that we think is reasonably predictable. We think, unless we do manage to cut emissions substantially, we're looking at increased greenhouse gases. We can emulate that in a very kind of simple way, just for conceptual purposes, by adding an extra term to those equations. So that's my equivalent of increased greenhouse gases, some extra sort of term, which I'll call the F forcing term here. And what you can see is that that term increases the probability of this state, of this part of the attractor, of the state residing in this part of the attractor, and decreases it down here. So 80%, 20%. So that's a key point, that the principle, and that's a point I'm going to come back to, that climate change in some sense is a different type of problem to weather forecasting. It's a force problem, or some boundary force problem, if you like, not so much an initial value problem. Just in passing, this question about the changes in regimes, is kind of relevant today because we're currently under the influence of what's called a blocking anticyclone, and have been for the last few weeks or so. And that very much was also the pattern that occurred last winter. You tend to get very, as you know, cold air. By the way, people make ridiculous things about blocking anticyclones. It's cold here, but it's boiling hot in Greenland. It's boiling hot in southern Russia. So, you know, you have to think globally when you think about these weather patterns. Just saying, oh, it's freezing cold in the UK, therefore global warming is off, slightly misses the point. But there is a more serious and scientifically justified question, which is kind of posed by that Lorentz model integration, which is how much more frequent will these types of circulation patterns be under climate change? And it's relevant particularly not only because of temperature and snow and such like, but our energy policy is based on significant move to renewables, and if the wind doesn't blow, then these things don't turn. So this is a serious problem to know how much more frequent these types of patterns will be compared to the normal westerlies which blow in, you know, the prevailing westerlies which blow in from the Atlantic. This is not a question that can be answered with a three-component Lorentz model because if one looks at the dynamics of these anomalous circulations, they're actually quite complex, and they involve, for example, the notion of breaking waves. You're familiar with breaking waves on a beach. These are breaking waves high up in the upper troposphere and lower stratosphere. In fact, this denotes a kind of mixing of stratospheric and tropospheric air through what's called Rossby wave breaking. And that does require quite substantial model resolution to capture that process well. And in fact, we currently think the current generation of climate models is not doing that process very well, which means we can't be terribly confident about knowing whether these persistent blocking anticyclones will become more or less frequent under climate change. All right, so just to summarize the main point, Michael Fish is doing an initial value problem, whereas the climate change is fundamentally a force problem or boundary type problem. Now, this is relevant to as I move my sort of circuitous route towards my point. So ensemble prediction has become a pretty standard tool in weather forecasting now for, I don't know, getting on for 20 years actually. It's also becoming a standard tool for climate forecasting. But now, as I want to talk about, for climate forecasting, we need to worry about more than just initial condition uncertainties. There are more uncertainties than just initial condition uncertainties. It's not just that we don't know the initial conditions. So the fact the system is chaotic does itself imply some uncertainty. It means I can't tell you on the 1st of July to 2100 what the weather's going to be like. I have to phrase things in a probabilistic way. But in a sense, that's not a major problem. We can deal with that through these multiple integrations with slightly different initial conditions. As I've already mentioned, the emissions, what treaties we manage to put into place will be important. That's an uncertainty as well. But we deal with that by using the word projections rather than predictions. So for each possible future emission scenario, we try and project into the future what the climate will be. And then it's up to the politicians and so on to decide whether they like that or not. The real third source of uncertainty, which I want to dwell upon here, is actually down to the models themselves, the mathematical representations of the equations of motion of climate, the uncertainties that are introduced when we try to solve these equations computationally. So these are the Navier-Stokes equations for fluids, basically Newton's second law. They're written here as partial differential equation. And at some level, one could worry about quantum mechanics and so on, but at the level of classical physics, we know, and after all, that's fundamentally what's important for this type of problem. These equations can be assumed to be known. The problem comes in how to solve these equations, because we need to solve them computationally, and what is done is project these onto some grid or other basis. So ECMWF uses spherical harmonic basis. I mean, there are other ideas, lots of ideas. But inevitably, you have a truncation scale, how small you can get down to. For a weather forecast model, that might be around 20 kilometers. But for a climate model where we have to go ahead 100 years or more, that's about 200 kilometers. So we can represent things on scales of thousands of kilometers or tens of thousands of kilometers down to maybe a couple of hundred. But if you remember that slide I showed you, the animation from space of all those those thunderstorm clouds bubbling away in the western Pacific Indonesian region, they're all occurring on scales actually quite a bit smaller than that truncation scale. And clearly they're important because they're providing the moisture into the atmosphere. They're determining clouds. And in fact, the latent heat release of the moisture as it gets converted to liquid droplets, that latent heat release drives a lot of circulations. So we can't just ignore them, and they're represented by instead rather, necessarily simplified equations, often called bulk formula parameterizations. We imagine that there might be some ensemble of these thunderstorm clouds within a 200 kilometer grid box, and we try to represent their kind of typical average effect on that grid box. Now this is really where the approximation comes in, because these formulae are not derivable from the laws of physics. They're approximations that have to be made just to make these equations computationally tractable. And one tries to put in plausible physical assumptions about these equations, and one appeals to observations. But in a sense, at the end of the day, these formulae are approximations. There's a bit of a, I dare say, dark art to the formulation of these equations. I'm dreading saying that because I can see the webcam looking at me and somebody's going to write in and say, don't say that. But in some sense, it is the case that there's no kind of objective procedure to come up with these formulae in such a way that they will be wholly accurate. And in a sense, it's this sometimes called closure. How do you close these equations, this equation with this formula? That closure process is what is introducing uncertainty into our climate predictions. The sorts of processes that might be, so this is an equation for momentum, the sorts of processes that we have to represent by these parameterizations, these subgrid closure formulae, things like turbulence in the boundary layer, small-scale turbulence around buildings and so on, and trees and forests and so on. Turbulence of a different sort forced by small-scale mountains or topography. The idea here is that these can actually, rather than just create turbulence in the vicinity, flow over small-scale orography can excite waves which can propagate either vertically or longitudinally, horizontally, and ultimately break somewhere quite remotely from the source region. So that's a difficult problem which is occurring on unresolved scales, has to be represented, and also the transport of momentum in these thunderstorm clouds themselves. Okay, so again, I want to just come back to IPCC because they're quite open about this. That because of this simplification that's necessarily needed in order to be able to solve the equations computationally, the models still show errors. So the models still show errors. This is chapter 8 of AR4. Although these are generally greater at smaller scales, important large-scale problems also remain. The bit I've missed out is a whole listing of those large-scale circulation patterns, which I won't dwell on because they talk about particular meteorological circulations, which people won't necessarily know. The ultimate source of most such errors is that many important small-scale processes cannot be represented explicitly in models, such as the thunderstorms in the tropics and so on, and so must be included in an approximate form as they interact with larger-scale features. And consequently, models continue to display a substantial range of global temperature change in response to specified greenhouse gas forcing. This is a slide I think I've shown before, but it just illustrates, this is from the AR4, showing the simulation of 20th century temperature trends. In observations is the black line. The models have, the ensemble average of all the models is shown here, and so there looks to be quite a good agreement between the models and the observations. But what is not clear in this diagram is that all the models here have been corrected for their biases against observations. So a little bit of a massaging. And if you actually didn't do that massaging, you'd see that the models have an enormous range of temperature, global mean temperature. So the biases of many models are absolutely enormous compared to the signal. And that's worrying, clearly worrying. And as a consequence, we also find, as the IPCC statement said, that there is consequently quite a range of future climate change predictions. Now, this was a study made by the climateprediction.net group at Oxford a few years ago, where people around the world could integrate one of the Met Office's climate models. And if you downloaded the model, you actually got a model with a very slightly different set of parameters. Remember the parameters alpha in my parameterization formula. So you've got a very slightly different set of these sort of external parameters alpha. And what they found was that with some parameter variations, you see, you'd like ideally to say, okay, well, we have to do this parameterization, but hopefully things don't depend too sensitively on these alpha parameters because the things are uncertain. Well, it turns out they're fantastically sensitive to these parameters alpha. And what they found in this project, that with some variations in the parameters alpha, they got up to 11.5 or even 12 degrees warming, global warming. I mean, absolutely enormous. I mean, we would cook, absolutely, if that was to happen. Now, the worrying thing was they couldn't reject those parameter values. This is a quote from the team at the time. No obvious problems with the high temperature models. Upper end has exploded. Okay, so what on earth is going on? Why is it so hard to produce a bias-free climate model, and why are things so sensitive to these parameters? So I want to just go back now to address that question back to my simple three-component model. Okay, and let's suppose let's suppose this was the truth, some sense. So very simple system. This is the truth. It fluctuates irregularly, chaotically between these two regimes. Okay, now suppose, let's say I came up with a model. I said, oh, I think I've got a model of that truth system. And I'm not going to tell you what the equation of my model is, but I'll just run it in time. I'll produce one of these X plots time series in time. And, well, you'll say, that's not a very good model, because clearly there's a kind of bias. The system is biased towards being up here. It should, the truth, according to the truth, it should spend as much time down here as up here, but it's clearly wrong. It's biased. There's something wrong. So now I ask you, okay, so there's something wrong with this model. What is wrong? What's the origin of the bias? What am I doing wrong in my model equations to make it have this bias? Okay, well, if you've been concentrating on my talk and you remember the bit where I used the Lorentz model before with that F term, you'll say, I know what's wrong. I know what's wrong with your model. Your model has got this F term in it, in the X component. If you subtract that F term from the X equation, you'll then go back to truth. So that I can diagnose, I can look at the output of your model and diagnose what the problem is. I can diagnose what the root cause is. So let's guess that the origin of the bias lies in the model's equation for X, i.e. the model equation. So I think I've been able to localize the source of that error. Okay? Well, okay, let me run the model. I'm going to run this model. I've actually already done it about 20 minutes ago or so, and it looks like that. Well, that model has this bias in the X as well. So it looks like I have nailed it down. I've nailed down the error in my model, or you've nailed down the error to this X equation. Well, actually, it turns out what I've done in producing that model, the bias model, is this one. I haven't added an F term here. I've actually subtracted an F term, and I've also I've added an F term here. So in fact, the origin of the error is not localizable in the X equation. It actually is spread over two equations. And if I were to subtract F from this equation to get back to truth, I'd actually be exacerbating the problem, because I'd be compounding this error with an even larger one in the X equation. Okay, just to make that a bit more clear, what I've done here is to write this equation slightly more generally, where I've got this parameter theta, which is an angle. And what I'm showing you in this figure is how the original Lorentz model responds by adding this F term with different values of theta. So if theta equals 0, cos theta equals 1, sine theta equals 0. So I just have this forcing term in the X equation. So that's the direction, if you like, of the F term as a vector. Think of F cos theta, F sine theta as a vector. So with theta equals 0, it's pointing in that direction. The system responds by moving in that direction. So the time mean state, instead of being down here, which it would be for the unforced Lorentz model, moves up here. So the direction of response is like that. Okay, let me change the direction now of this forcing term to pi upon 4. Now we find that the direction of the vector F and the direction of the response is the same. Right. Let's now do this another experiment where the forcing is now purely in the y direction. Again, the system responds by moving in this direction. It's not moving in the direction of the forcing at all. It's moving in a direction which seems to be the same roughly for all, no matter what the forcing is. And in fact, even if we did this, and this was actually what I call my bias model, the forcing F was actually in the plus y and minus x direction. And again, the system wants to move off here. So what on earth is special about this direction, this sort of diagonal direction in the xy space? Well, it turns out that this is the direction of the leading eigenvector. I seem to have lost my... Oops, has it run out? Okay, no, it seems to bust. Okay. Old-fashioned, yes, that'll do nicely. This direction, it turns out, is the direction of the leading, it's called empirical orthogonal function, or it's the direction of the preferred internal mode of variability of the Lorentz system. the leading eigenvector of the covariance matrix. So somehow there's a link, the system wants to respond by moving in the direction of its leading internal mode of variability. Okay, I'm going to pass over this because I'm a little short of time, and just say this is exactly what happens when we look at rather more complex models. So the leading mode of variability in the northern hemisphere flow is a thing called the northern annular mode. So we get things like, when it's in a positive phase, we get enhanced westerlies. When it's in a negative phase, these westerlies become much weaker. So in some sense, well, last winter actually was a great example of when the system was in this phase of the northern annular mode. Now, this is a picture of systematic error from my own institute's long-range forecast model, seasonal forecast model. And you can see the similarity, I think, between, this is in terms of pressure, these are pressure perturbations, so negative, positive. Very similar to that pattern. We're seeing the error projecting onto the dominant mode of variability of the atmospheric system. Now, this is making diagnosis of the cause of the errors very difficult. And just to illustrate that, and conscious I'm running out of time, I'm just going to show you 3 experiments where we did 3 very different things to that ECMWF very complex climate model. One is changing these it's actually the parametrization of the deep convective clouds, part of the subgrid parametrization, changing that. Here's another one where we sort of are changing the numerics. We actually increase the resolution by a factor of 5. So sort of not changing the, as it were, the subgrid parametrization, but the numerical structure of the model. And here's a third one, which is something I'm personally very actively involved in, which is, if you like, changing the structural form of the equations to make the model actually more stochastic. So there is, in some sense, adding stochastic noise to the model. But the remarkable thing is the response, I mean, there's clearly differences in detail, but to first order, the response of the model to those 3 different changes is very similar, and indeed, you can see, at least roughly speaking, it's projecting onto that northern annular mode. In other words, we're seeing with a 10 million degrees of freedom model the very same thing that we saw with the Lorentz model. This intrinsically, the intrinsically preferred way in which the system responds by projecting onto its principal modes of variability. I think one way to understand that is actually something Einstein did in 1905, but not his 2 famous papers, but he had this third paper on Brownian motion, where he made the point that the same random forces which cause erratic motion of a particle in Brownian motion would also cause drag if the particle were pulled through the fluid. And that became embodied in a thing called the fluctuation dissipation theorem, which is a very general result in statistical thermodynamics, which links the response of a system to an external forcing to its internal fluctuations, to the system's internal fluctuations. And that's what we're seeing here, both in the climate system and indeed in those even simpler Lorentz systems, which probably don't satisfy this theorem precisely. And so there's a kind of degeneracy here that you can do different things to the model, and when you look at its most basic response, it's always very similar. It's in the terms of the primary modes of variability. That's what's making diagnostics so difficult. That's the basis of the IPCC comment that simple diagnostics of model error it's very difficult to deduce from them what the root cause of the problem is. So in the last few minutes, I want to just Take five, thank you. I want to just return to data assimilation. So I showed you that slide because the question is, how can we overcome this, let's call it the fluctuation dissipation theorem constraint? How do we overcome this to really understand model problems? Okay, so I showed you that slide, which is kind of the ideal data assimilation situation. But suppose we had instead we did data assimilation with a biased model. So again, remember, these are the observations. Here's an analysis. We move it forward in time, and then we combine the observations and that projected state. We do it again, the data assimilation produces that projected state, and again. Now you're seeing in this case with the model bias, there's this kind of, instead of it just being, as it were, instead of sometimes the analysis sometimes the data assimilation moving this first guess up to here and sometimes down here. Now we get a systematic movement. Now in this is 6 hours of a forecast. So the issue is that in that 6 hours there isn't enough time for whatever errors there are in the model to project onto these dominant modes of variability. The problem with the fluctuation dissipation theorem is it takes, you make an error in the temperature equation, then that starts to feed into the momentum equation, the waves propagate around the globe, they affect everything. That's where you get this projection onto the dominant modes of variability. It's an asymptotic problem. If you can restrict the problem just to a few time steps, then you really can localize the problem to the temperature equation, to the Western Pacific, wherever it happens to be, in ways that you can't do by diagnosing the performance of the model in its asymptotic state. So data assimilation is a way to get round the constraints, I would call, of the fluctuation dissipation theorem. So we did that. This is a paper by a colleague of mine, Mark Rodwell, looking at this climateprediction.net work. So this is some predictions of this is going back to that one where people ran the model with different parameters. And these blue dots are all ones where there's a certain thing called the convective entrainment parameter was reduced. And these were all producing these enormous global warmings of 9, 10, 11, 12 degrees. And these were, and the problem was that the bias, just the straight sort of 20th century bias of these models wasn't much different to the standard version of the model. That's why these authors couldn't easily reject these models as being inaccurate or unnatural somehow. So, very briefly then, because this has got too much information in it, but this is a result from our paper. And the key point here is to look at this red curve here, which shows that in the tropics, in 6 hours, the fact that there's this kind of offset of this line from zero means that the model has got very substantially out of balance with that perturbed parameter alpha, the entrainment parameter perturbed, in a way which doesn't happen at all with our control model. So basically, we were able to say, based on just a set of 6-hour weather forecasts, that these very extreme global warmings 100 years from now are very unlikely. So can a 6-hour weather forecast determine the climate 100 years from now? Well, I don't know if it can determine it, but it can certainly constrain it substantially. So the last part of my talk is, why don't we then use these ideas in climate prediction? Let's just do it. Put data assimilation in. We run the models over short time steps, changing parameters. We look at how the initial imbalances are set up. We can maybe constrain clouds and water vapor in ways that are just impossible to do with looking at the long-term asymptotic evolution of the model on its own attractor. Well, there are problems, and I'm running out of time, but basically, from 1950, this was the famous Princeton group, set up the first weather forecast. There was a chap who's not in this photo, but I think he was one of the part of this early team, called Norm Phillips. He was the first one to realize that weather models could be actually used to look at climate, to look at long-term climate, not just looking at the next couple of days ahead, but looking at how long-term climate behaved. And from about that period in the mid-50s, the two systems have diverged enormously. And in particular, no IPCC fourth assessment model that I'm aware of had data assimilation capability. Now, the reason no model had data assimilation, no climate model had data assimilation capability was primarily because, as I said to you, climate change is not primarily an initial value problem, so people didn't think that was a high priority. And moreover, their priorities were to develop models which had all sorts of complex things like, sulfate aerosols and carbon cycles and chemistry and such like. So there were enormous demands on human resources. Oh dear, the dreaded another hour. So human resources was sort of three reasons why it hasn't happened. Climate, not an initial value problem. Human resources, enormous. And the other thing was, well, you know, climate centers have computers, and they have all sorts of priorities for computing power. They need to run decadal, centennial, ideally run paleoclimate integrations to test the models in paleo mode. They want to run multiple ensemble integrations. They want to get down to resolutions where, for example, that Rossby wave breaking can be simulated. They want to get the interchange of the stratosphere and the troposphere and the mesosphere and the stratosphere right. They want to get chemistry, aerosols, carbon cycles right. So data assimilation has been typically not the highest priority because there are many other demands on computing power. So, in the last 2 minutes, I want to come back to realizing I've slightly run out of time, but I really am kind of concluding. Can climate scientists do more to reduce uncertainty? I think they can, and I've given one example how this could be achieved, which is basically a much more integrative approach between weather and climate forecasting. Currently, the weather and climate forecasting communities are not well integrated, and I don't think making good enough use of one another's expertises. But there's another issue here which I'm going to raise, which is many institutes around the world view. So this is the other issue is about human resources. Freeing up the human resources to allow this integration to take place. And here we have another problem that many institutes around the world view their climate models as matters of institutional and sometimes national pride. Now, okay, that's a good thing, but the downside is that as a result, individually, these institutes do not have the human or indeed computational resources needed to make, I believe, significant inroads into the problem of reducing climate uncertainty, and, for example, integrating some of these things I've talked about. And in practice, such resources are often used just trying to duplicate developments done elsewhere. So I see that as where the scientists could do better. And one idea which I think is good for discussion is whether a much more community-wide approach to climate model development would enable these human resources to be made better use of. But as I mentioned at the beginning, I think there's the question about can we do better has to be seen also in the context of can governments do better, and maybe the private sector can also help here, because after all they are being affected by future emissions cuts and so on, as well as the ordinary person. And here I just want to say this issue about computing is a really serious one, and currently the current proposals, particularly in Europe, for high-performance computing for climate, I think are wholly inadequate. I showed that very briefly because I've run out of time, but I showed there's many demands on computing, and that poses a real problem, and it really does pose a problem in implementing the ideas I put forward about data assimilation into practice. So I think governments should work together much more than they are currently doing to provide real leadership scale computing, the kind of petaflop, soon to become exaflop computing, dedicated to the climate community. And this was something Nature picked up a year or so ago. Governments should work together to build the supercomputers needed for future predictions. So I think this is absolutely my last slide. Discussions on global emissions cuts appears to be reaching stalemate. And I do think we have to ask the questions, are we doing all we can to reduce uncertainty? Because I think that's what is going to be needed to move policy forward. But as I've tried to point out, this is by no means a straightforward question. So over the coming years, I think we do need a renewed effort by scientists and by government to really ask, are they doing all they can to focus on this problem of reducing uncertainty? I would like just to make a quick plug to the Newton Institute, because I think these types of mathematical multidisciplinary programs are really important to try and move this whole problem forward. So I think the Newton Institute's done a wonderful job the last few months in engaging actually a much broader range of people than would, say, typically be at a climate type of workshop or conference. And I think having this broad, engaging mathematicians and so on is really important in this area. But I think also to move forward, governments have got to now do more collectively to provide the technology to enable these types of new innovative methods to be put into practice. So I've sort of given you a little bit of science, but also some topics that we could maybe talk about over a glass of wine. So apologies again for running late, and thank you very much.
I think we should allow a few minutes for questions, I guess. Yes, please.
Well, you didn't mention the costs of data assimilation. So I'm coming from ocean modeling community, and in this community, data assimilation is probably the last thing on the list of what oceanographers want to do. And the reason is very simple. It's completely unfeasible now to simulate data in an eddy resolving ocean model. And nobody wants to sacrifice this capability of resolving eddies in the ocean.
Yeah, I mean, you've put your finger on a good point. You know, I talked about resolution for the atmosphere, but I could equally talk about it for the ocean. So climate institutes are given a computer. Here's a computer. What do you want to do with it? They'll make all sorts of list of things, and in your case, they may say, I want eddy resolving, models, and that's where the resources go. And it's right, the data assimilation is computationally complex, and I said, it costs more. The single biggest computational cost in the 15-day weather forecast is the data assimilation part. So even just getting to time zero, that's the most important part. So yeah, how do we break this down? We have to make sure we have the resources to do all of these things. I mean, either it's an important problem or it's not. If it's an important problem, please give us the resources to solve it.
So if I was in the position of giving you the money for the bigger computer, I might ask, so how much should I give you, and how much uncertainty are you going to be able to reduce if I give you 100 times more or 100 times more? Is it linearly related? I suppose my question is it possible to answer that question at this stage? Is it possible to know if we could get a tenfold increase in compute resources, how much that would reduce our
I don't think, unfortunately, I often give talks where I say, the Navier-Stokes equation is actually one of the key kind of $1 million problems that the Clay Mathematics Institute put forward. It's up there with the Riemann hypothesis and all these things which haven't yet been proven. So we don't have a profound theoretical understanding of things like convergence issues for Navier-Stokes. So the question is, for example, as you reduce, as you increase resolution, as the truncation scale gets smaller and smaller, how better do you resolve? How better do you simulate climate? How much do your metrics of error reduce? We don't have that kind of meta theory to tell us. Unfortunately, it'd be great if we did, but we don't. So, unfortunately, we just have to say this is a critical problem for society. We have ideas about how to do better, but we need the funding in the technology to enable us to put those ideas into practice. And without it, we can't.
And if I can add a comment, I think it's an example from lattice gauge theory and particle physics, and we started that game 30 years ago, and 25 years on, there were such dramatic advances in the algorithms, that's the way that the equations were integrated, they got a step factor of 100. 25 years on in the implementation and study of these kinds of models. So just in the numerical implementation of this time stepping and so on, I don't know what, I think that is an equal unknown in terms of in progress that one might be able to make. There was a question here, yeah.
Yeah, Nadia Pinari from University of Bologna. So thank you very much for the very challenging. So I wanted to ask you two questions. The first one, intuitively, since I believe oceanographers have done a lot of data simulation in the last years, and we have now operational ocean forecasting in place. Intuitively, it's clear that we know much more when we do assimilate the data in the ocean, which is much more nonlinear than the atmosphere. So it is, I would say, important.
Not sure about that.
One point is, well, from a v.grad v, it is more. If you want to say, but let's say what is the correlation between what we do in data simulation? Because you put it there and you show some example. Is it really because you use weather forecasting to practically do the stochastic models of the physics, and then you reparameterize that in climate? So what is the deep meaning of getting the weather connection to the climate? That's one. And the second question is, it looks like there is no importance of doing super ensemble then. super ensemble is really something that will obscure for many more years to come the real problem of what climate change uncertainty is.
Can you answer at least one of those?
Okay.
Because you've got another question up here.
Well, I don't know if I fully understood your first question, but my comeback to my point is that in data assimilation, I think it allows you to isolate errors in the representation of physical processes in the models in a way which the traditional asymptotic evaluation of climate biases does not allow you. I mean, Matt Collins gave a very nice talk before tea, sort of illustrating this problem. We can do all sorts of EOF analysis of the systematic errors of these models, but relating those to the basic physical errors in physical processes is extremely difficult for reasons I've tried to say. And I think data assimilation allows you to do that. But it's a non-trivial problem putting data assimilation into a climate model. It requires manpower and human resources and computer power.
I think I'm going to allow only. Okay, I think maybe just one more, and there'll be a good chance over the wine, which is this final question, David, is between everybody and a glass of wine. So,
short question then. There's an assumption that the prediction errors for climate change are somehow related to the short-term forecast errors, and that's an assumption, right? What's the assumption? You could have a system that had wonderfully no bias on short-range drone forecasts, but again, allows you climate
Yeah, that's right. No, the assumption, I mean, I tried to earlier on put, hold with one of these sort of triangly things, all sorts of processes, carbon cycle, chemistry and so on, cryosphere, all these things, which would not be addressed by looking at very short-range biases. So the premise is, to come back to my sort of key point, that I think what is the primary source of uncertainty, at least for sort of predictions up to 2100, are these water cycle feedbacks, the water vapor and cloud feedbacks. Now these are occurring, clouds occur on very fast timescales. The feedbacks may be very long timescales, but the processes that generate clouds and dissipate clouds and so on are fast timescale processes and are amenable, I think, to this type of analysis. So I'm very much focusing on my thoughts on this kind of key, the top bit of that figure, wherever it was, that was addressing the water cycle. And I acknowledge that there are other, more the biogeochemistry problems, which are much longer time scale. I mean, arguably, there could be some, data assimilation in Earth system models more generally may start to address some of those longer timescales, but that's less clear. But I think the key point is that this provides a really, I think, potential tool for the fast.
Radiated response to the clouds on longer timescales that you didn't pick up on the short-range forecast errors as well. It's a necessary but not sufficient condition you're looking at.
Well, I come back to my point. Most of the cloud processes occur on fast timescales, so and this is where most of the uncertainties are.
I'm sure there are lots more questions, but forgive me, and I'm not going to eulogize. It was just a great talk. Thank you very, very much.